Sounded like a genius in class.
We were there for it.
Yeah, but without the recording, though, you can. Yeah, it didn't record, but I was brilliant. I was on the verge of a Nobel Prize there.
Trust me.
That's right. It's like Nixon is missing 18 minutes. All right.
Yeah.
All right, so I'm dealing with an area here and an area vector. I got an electric field. So again, can't remember what time you walked in, Freddie, but the electric field shooting across like that. So imagine these arrows shooting across, and then I get some maximum amount of penetration of the arrows through this paper like this, minimum like that. Which one would be more appropriate to describe this, what I'm trying to get to of what eventually is going to be called electric flux? But it's a measure of how many arrows pierce the paper.
You get more the more perpendicular it is. So.
You get more the more perpendicular it is. So if I'm dealing with the area vector though, which direction is the area vector here?
Same direction as the flux.
Okay. An area vector here.
Perpendicular.
So which one, since I want that to be 0 and that to be the maximum amount, which multiplication operation do I want?
Toward.
The cross product?
Yes.
So what is the cross product between the area vector and the electric field? Given the electric field is going that way, my area vector is going that way. What would the cross product be? Let me draw it down, or up, or here. Got my electric field shooting off to the right. I got my plane, my surface right there, and the area vector going that way. Which is going to give me a maximum amount. Dot products or cross products, if those are the directions of my area vector and electric field.
It looks like you've drawn the area to be like this, right? As opposed to this or this.
I've drawn the area, drew the area that way. My
I must be.
piece of paper is like this.
Okay.
If they're both going in the same direction, is it just the area vector times the electric field?
Yeah, which one?
What do you?
I got two ways of multiplying.
Right.
They're vectors. Two ways of multiplying vectors. Dot and cross. That's the question I'm asking is which math operation do I want to use?
The cross product.
I feel like it'd be the dot product because the area vector and the electric field are pointing in the same direction, so they're parallel, right?
They are parallel. Cross products of parallel objects. Because remember, cross products is like perpendicular. If these are parallel, no torque.
Okay. So if you were holding the paper this way, the area vector was facing up, then
Yes.
you would use the dot product, the cross.
No, we're still using the dot product, but if my paper's like this, area's pointing up, electric field's that way. What is the dot product between perpendicular?
It's zero.
Yes.
Right.
So when my paper is like this, I get 0 when I multiply. When it's like this, I get my maximum amount.
Right.
So we're not doing a cross product this way because I want it to be 0 like this. When my paper's flat, I want to get 0 if my electric field's going that way.
So we use the dot product.
Yes. Yeah, that's ultimately where I was going on that. So I'm going to define this thing called electric flux. It is a capital phi. I think it's an A there. Capital phi. With a little subscript E here. This is the electric flux. And it is equal to E dot A. Or if I'm dealing with a small little section of area, well, then just my area is smaller there. And just a 10-second aside. If you can count to. Integral or antiderivative, this is just the fancier way of writing. You're going to add up E dot EI dot AI. If I've got a multifaceted surface, I basically do the E dot A times each surface and then I add them all up. That's just the fancy way of doing it. When you see the integral in this, you're adding up an infinite number of infinitesimally small things. And it comes out to some number. There is, actually, I think it's a master set problem where I do have two surfaces. I think I have the surfaces like this and an electric field coming in like that. And what you would do is you find the electric flux through one surface and the electric flux through the other surface and then add them together.
Is that supposed to be delta area vector?
Say it again?
Is that supposed to be delta area vector?
Yes. Actually, instead of writing delta area vector, I just put a subscript I here to indicate it's the area vector of some small piece. All right, so if I'm looking at my surface here, and I find the area here at point P, my area vector at point P points out because this is a closed surface. And then there's some value of E there that's, well, frankly, the magnitude of E is the same everywhere I am on here because they're all equidistant from R, or my charge Q, a distance R for my charge Q. So whatever the area that is, then I got an area here, I got areas all over. So basically I'm taking my electric field, which is the same at every point on here in magnitude, times my area vector. I add them all together, I basically end up with whatever the magnitude of my electric field is, times the area of the whole thing. Because no matter where I am on the sphere, my electric field and the area vector at that point are always in the same direction. So formalizing it slightly, it's the sum of the electric field at any point I, dot product with the area at any point. So the area of some tiny little section right here. My electric field dot product, they're always in the same direction no matter where I am on the surface of the sphere. They're always pointing the same way. And so this just becomes the sum of E, I, K, I. My electric field is the same magnitude everywhere, so I can factor that out. And so this is just the sum of all those tiny little areas all over the place, which is just the surface area of the sphere. So this becomes E times 4 pi r squared. Questions to hear? I've seen at least one furrowed brow.
Are we still going over the derivation? Is that?
This is part of the derivation.
This is the derivation, okay.
I'm going to do it specifically for this case,
Uh-huh.
and then I'm going to say, do the hand wave and go, and it works for any closer.
Okay. Yeah, I'm good with the hand waving.
You don't want to spend a couple of days learning calculus and vector calculus?
No, not particularly.
Okay. Last weekend, sure, but there were snow days.
Right. Snow makes a difference.
Now, my electric field, though, we already know what the magnitude of that is. That's where we started off. My electric field, all right, so I got phi E. My electric field is 1 over 4 pi epsilon sub naught times q over r squared times 4 pi r squared. And this will simplify. Because wow, 4 pi r squared, what a coincidence. And I'm left with that charge in the middle over epsilon sub naught. Recognize if I had k in this problem still, then there'd be an extra factor of 4 pi showing up. So for a charge at some point in space, we got ultimately the flux is just whatever that charge is divided by this constant. Now the hand wave. It turns out the electric flux through any closed surface has to be a closed surface. And again, the electric flux is just the sum of E sub I, A sub I. And I put a little circle there just to indicate a closed surface. In the integral, if you see that curve that I had done when I did the calculus version, if there's a circle there, that means we're dealing with something that basically wraps around on itself. So if you're doing an area, if area is involved, then you're doing a surface area. If it's a line, then it's a loop that connects back on itself. That is equal to whatever charge is enclosed in the surface divided by this constant. This is Gauss's law of electricity. Later on, we'll do Gauss's law of magnetism.
After the Q, did you write something to abbreviate enclosed? Is that what that meant? The subscript after Q, is that just referring to anything that's enclosed?
Oh, yes, enclosed. Yeah. So, for this particular surface over here, for my sphere, we had that charge smack dab in the middle. And now I come along and I smack this charge. So it is now over here. Now the radius of my circle or my sphere is still r, that hasn't changed, but I now have q over here. What's the flux, electric flux through the surface now?
It's not the same throughout now. Is that correct?
It's no longer symmetric. The electric field at any point on the surface is no longer this
Symmetric.
same magnitude.
That's not what you're asking.
I'm asking for the electric flux, not the electric field at any point, but the total E dot A, the total electric flux through the surface now that I've knocked Q from here to here. And the answer is, it's not zero, not that simple, but the answer is simpler than you're thinking right now.
Is it still the same even though the
Yes.
magnitude's different?
It is indeed still the same because the charge is still enclosed. Yes?
I didn't ask this earlier, but what is that subscript after Q? The you got the Q.
Right here,
Yeah, what is that?
ENC for enclosed.
Okay.
Sometimes they'll write N for inside. Clever the way they did that. Let's actually come up with some numbers here. So let's make this charge.
Did the magnitude stay the same when you moved it over?
5 nanocoulombs. And actually come up with what the electric flux is.
Well, it's not the charge itself. But then when you just moved it over, it's still fine.
So I don't have to think through, well, what's the electric field at all over this place? If all I'm asking is what's the electric flux, then it's just that enclosed charge, so that's 5 times 10 to the negative 9th, divided by epsilon sub naught, 8.85 times 10 to the negative 12th. And if someone would be kind enough, give me somewhere under 1,000. So 500 80.
I got
I got-
basically 565.
Yeah, what do you get?
565.
565.
I got the same thing.
Units. Let's talk about units now. Because that was 5 coulombs and this was coulombs squared per Newton meter squared. What are my units here?
Just
Coulombs
Newton,
over Newton's, time.
Newton meter squared.
Sorry, in a single voice, that'd be cool.
Coulombs per Newton meter squared,
Coulomb per,
Newton meter squared.
no. You are,
Newton meter squared per coulomb.
there we go. It should be the units of electric field times the units of area, so that'd be Newton per Coulomb times meter squared. Over here, the Coulomb does cancel out, but this is the denominator. Dividing by a fraction, same as multiplying by the reciprocal. So this would be coulombs times Newton meter squared per Coulomb squared. And you're left with Newton meter squared per Coulomb. And the physicists and the powers that be looked at this and they said, yeah, we can deal with that. We're not gonna come up with anything else.
When I solved for this, the charge of Q over the constant, I got like scientific notation for like to negative 22. I got the like 565, but.
Oh, you got a negative 22. I'm suspecting that you did 5 times 10 to the negative 9th divided by 8.85 times 10 to the negative 12.
Yes.
And you forgot to put parentheses around 8.85 times 10 to the negative 12.
Yes.
Because then it just divided by 8.85 and then multiplied.
Yeah, I see. Okay.
So now, so that's the charge, that's the electric flux through that surface, no matter where Q is, as long as it's inside. Now, I'm gonna add another charge here. 10 nanocoulombs, let's make it negative 10 nanocoulombs, right here. What's the electric flux through the surface now?
I'm sorry, is that the new Q or is that just the point charge?
It's, this still here, I'm just adding this, we now have 2 point charges. Q right there, and then my new one right here.
If it's not enclosed, does it impact the electric flux of the sphere?
It's not enclosed,
It's not
so
enclosed, so it seems like it wouldn't be involved in the formula, so would it not impact the electric flux of the sphere?
it would not. We get the same answer, 565 Newton meter squared per coulomb.
Why does it not impact it?
Ultimately, if you think about, you know, I got this point, and you think about electric field lines going through a surface, or either emanating from or going towards the point charge. So this one has electric field lines going in every direction. This one has electric field lines going towards it, but any line that goes towards it, if it passes through here, it's gonna pass through there. It basically enters the surface here, exits the surface there, and that ultimately makes the electric flux from this 0, because this is gonna be some negative flux, that's gonna be some positive flux,
And it cancels out.
and it cancels out.
So because it's not enclosed in this sphere, it's,
Then we don't care,
okay. Cool.
at least as far as the electric flux is concerned.
I love not caring.
Okay.
You might have already gotten over this, but conceptually, what exactly is the electric flux?
It is a measure of how much penetration an electric field has through a surface.
Okay.
And it will allow us to derive electric field for some nice objects.
Gotcha. And when you moved the the charge was initially in the middle and then you moved it to the left, it kept its same magnitude, you were saying, is that?
When I knocked Q,
When you knocked Q?
yeah, I kept
It's
the same
just
magnitude, all I did
okay.
was just
Just
do a hand of
okay.
God to move it.
Gotcha, okay.
Other questions? Yes?
You said an electric flux conceptually it's a measure of how much an electric field will penetrate an object. Is that what you said?
Surface.
A surface. Thank you.
And at this point, you probably could guess what magnetic flux is. But that's for a
How
later
much a
chapter.
magnetic field will penetrate a surface?
Yep. Now let's actually use this. Use that. I have an infinite line of charge. With linear charge density lambda. If you think about what density is, sort of the mechanics of density, it's mass divided by volume. Charge density, without more adjectives or restrictions, is charge divided by volume. Surface charge density, charge divided by area. Linear charge density, this is time for unison. In unison, linear charge density is
Is it like charge divided by like the slope of the line?
not slope,
Length?
length. Yeah. So when I'm saying it's a linear charge density, actually I throw in uniform linear charge density. I'm saying that it basically gives me a charge per unit length. So if I take a segment right here of whatever length that is, I'll have a certain charge on it. If I take that, I should get more charge because the ratio of charge to length is the same regardless of how much length I pick on this line. So how we use Gauss's law is we create what's known as a Gaussian surface. So I have this line of charge here, and it's just a line there with a lot of charge on it, but I'm going to make believe that I have a surface there. A Gaussian surface is a virtual surface. It's a make